talk about SubWeyl Subconvexity and short p-Adic exponential subs.
Okay. Well, thank you for the introduction, and thank you all for coming. It is a great honor to be here, and I'm sure you hear that quite often around here. Okay, so the topic of this talk is related to a subject of central interest in modern number theory, and it is about the distribution of the so-called central values in families of L-function. So as a classical example of this, I would maybe start off from the Riemann zeta function. The Riemann zeta function is initially defined by the absolutely convergent series 1 over n to s. And it actually has, also it can be written as an infinite product over all primes, 1 minus 1 over p to s inverse. And so this representation as a so-called Euler product is what's responsible for the fact that the analytic properties of the Riemann zeta function somehow dictate many of the interesting phenomena about primes. Okay, so Riemann proved that this zeta function actually possesses an analytic continuation to the entire complex plane. It has a pole at s equal to 1, and it has a functional equation relating the values at s and 1 minus s. And so a question of classical interest then is to understand the distribution of values of the Riemann zeta function along what's called the critical line. So that would be the distribution of values zeta of half plus it. So that's a vertical line where real part of s is 1/2. And so you can ask many questions. You can ask, for example, when is this 0? Right? That would be related to the Riemann hypothesis. You can ask how often is it 0. You can ask how large is this on average. You can ask how large does it ever get? How often does it get very large, etc. And it is this second circle of questions that I'm going to be interested in. So I'm going to want to know how large can this possibly get. And it turns out that the correct scale on which to ask about this problem is to ask for estimates of the form zeta of half plus it is less than 1 plus t to theta plus epsilon, where epsilon is an arbitrary positive number, and this means that there's an implied positive constant there. Okay, so one wants to understand what are the allowable values of theta here, i.e. what is the infimum of all the exponents that you can put here so that this bound holds. And it follows from Riemann hypothesis. I'm going to leave a little space here. So it follows from Riemann hypothesis that this holds with theta equal to 0. And this is known as the Lindelof hypothesis. It lies very much out of reach of the current methods. What is known is, as the simplest estimate that's known, you can use just the analytic properties of the Riemann zeta function, shift contours, and use what's known as the Fragment-Lindelof convexity principle. And you can prove that this holds with theta equal to 1/4. So this goes under the name of convexity bound. And this estimate was improved initially by Hardy and Littlewood in maybe 1916 or so to theta equal to 1/6. So this is due to Hardy and Littlewood. And they used a technical device that's known as the Weyl differencing. It goes back to Hermann Weyl. Okay, so this stood as the best estimate for a while, and then it was improved by Wallfisch. I believe he was the first to improve this in 1924 to the value of theta of, okay, maybe a little here, of 163 over 988. You can see that I prepared, which is approximately 0.1650. The point being that it's a little less than 1/6. So it improves upon this bound. And then there was a bunch of results that followed that incrementally improved this estimate little by little, including a very important paper of Bombieri and Ivanets. And down to the current value of theta is 32 over 205, which is approximately 0.1560. So this is due to Huxley in 2005. This, I believe, is the current record. Okay, so the progress has been incremental and modest, but there has been progress. Okay, now for a modern and general perspective, one would actually look more generally at any automorphic representation over GLN. I'm going to be brief here. Don't run away. So GLN. And to this automorphic representation, you can associate an L function, L of S pi. It is part of this big Langlands program that we basically expect that these so-called automorphic L functions encompass any L function that's ever going to be written, at least if it's of any interest. And then, for our purposes, another important notion is the notion of the analytic conductor of this representation, or of this L function, which was introduced by Ivanets and Sarnak around 2000. So this analytic conductor is supposed to measure the complexity of your L function. It's a positive number, and it's supposed to take into account the complexity, or as we number theorists would say, ramification, both at infinite places, that would be kind of this T that we're seeing here, and at finite or non-Archimedean places. Okay, and the idea is that this number should govern many of the analytic properties of this L function. So in particular, if we look at central values of this, a value at a point half, then we are interested in bounds of the form the analytic conductor of pi to theta plus epsilon. And as before, theta equal to 0 is implied by the grand Riemann hypothesis for this L function. Even more out of reach of the current methods. Theta equal to 1/4, I'm going to be careful here. So theta equal to 1/4 is expected to follow from the analytic properties of pi. I don't think I'm going to be brave enough to say that it follows. Okay? But anyway, this is what we would call the convexity exponent. Well, people have, okay, we can talk about this later. Okay, fine, it's known. The point being that, so certainly in lower dimensional cases, if you look at GL2 or GL3, it is known, and it carries no arithmetic information. So it turns out that very often we can actually prove an estimate like this with theta a little bit less than 1/4. And such a bound is known as a subconvexity bound. And in those cases in which it was proved, it often carries spectacular arithmetic consequences where you can use it in view of the full power of the grand Riemann hypothesis. Now, the way these things usually work, at least more recently, is that somebody goes out and works on a subconvexity problem and comes out with a paper in which they prove this estimate with theta that's like less than 1/4 by something like 1/20,000 or something like that. So usually the first exponent is very, very, very close to 1/4. But then people look at this and think a little more about what's important and understand, okay, there have been losses here and there. These are important points. These are not important. They brush up things. And then often this exponent goes down to something more reasonable and recognizable. And in particular, in a number of instances, not too large of a number, but in several instances, the exponent of theta equal to 1/6 was obtained. For example, if you look at GL2 L functions in the T aspect, then such a bound is known. And this exponent goes under the name of Weyl exponent by the analogy with the zeta function case where it is obtained by Weyl differencing. But what I do want to say at this point is that this exponent has somehow achieved the status of a gold standard. Somehow nobody has yet ever proved a bound like this with theta less than 1/6, except in this one case. Right? So no other L function has ever gotten an estimate in which this theta was less than 1/6. And consequently, when people get to 1/6, we kind of feel that we've understood the problem and that that's it, and that we're not going to get any farther. OK, so of particular interest for me will be the following case. So I'm going to take chi to be upper. I'm going to take chi to be a character, a Dirichlet character, modulo q. And I'm going to be interested in central values of the Dirichlet L functions associated to this character. Okay, so the bound that is of interest is to bound this by a power of q. Okay, so q is the analytic conductor for this problem. And as before, theta equal to 1/4 is the convexity exponent, which follows easily from the functional equation. Theta equal to 0 is expected and hoped for, but completely out of question with current technology. Now, what is known, and improvement on convexity is known, it is due to Burgess back in 1962. And it gives the exponent theta equal to 3/16, which is equal to 0.1875. You will notice that this is more than 1/6. And it is frustrating. I mean, it depends on whom you ask, but certainly there are many people who are very frustrated by the fact that we can't break this bound here.
Could you write that L function out explicitly?
Oh, yeah, sure. So the L function in this case would be given by L of S chi is sum of, actually, thank you for reminding me to do that, chi of n over n to s for real part of s greater than 1. Right? Right now, Q is anything. I'm still introducing things. OK, so, I mean, the reason. Yeah. So the reason why this is frustrating is that we have GL2 L functions for which we can prove better results. And somehow, this should be a simpler problem. But it's not. OK. However, the Weyl exponent is known in two cases. So theta equal to 1/6 is known in the following two situations. So the first case in which it is known is, let's say, if you take p a fixed prime, and then you consider characters chi modulo p to n, where n gets large. So I'm going to look at L of S chi, where chi is a character modulo p to n. P is fixed, let's say 3. And then you look at characters modulo 3 to n, where n gets large. So in this case, the Weyl exponent is known for n large. And this goes back to a paper of Barban, Linik, and Chudakov. And they actually use some ideas that were introduced by Postnikov. So I'm going to add Postnikov here, even though he wasn't really involved in the subconvexity aspect. But he really introduced the ideas that went into this. And then later on, this was generalized and uniformized. In particular, there was a paper by Fuji, Gallagher, and Montgomery. And then there was also a wonderful paper by Heath Brown that went out in Invenciones in '78. So in particular, Heath Brown proved a Weyl exponent, say, for characters modulo p cubed. OK. So this is one class in which the Weyl exponent is known. And the other class in which it is known is, by very different techniques, is when chi is a quadratic character. So this was a brilliant paper of Conry and Ivanets that appeared in the Annals around 2000, I believe. So these are the two situations in which the Weyl exponent is known. Yeah, it's a very, very different situation. Yeah. OK, but what I do want to point out once again is that this was all down to the Weyl exponent. And so what the main result that I'm going to state right now is going to be about going beyond this barrier. So the theorem is as follows. So for any, or maybe for every theta greater than particular constant theta 0 that I may define later, is approximately 0.1645. The point being, it's less than 1/6. There exists an R such that the central value of this Dirichlet L function is bounded from above by p to r times q to theta times a small fudge factor, log q to a half. And this holds true uniformly for every character chi modulo any prime power q. So q is p to n. Okay, so there are two things that I want to mention before we move on. So the first thing that I want to mention is that for n large, so if you think about n getting large, this beats the Weyl bound, because the Weyl bound would have 1/6 here. Right? So this is the Weyl exponent, and this is the first and only family of L functions for which such result is available, except for the Riemann zeta function. Okay, and the second thing that I want to mention is that this is uniform in P. So the implied constant is uniform across all prime powers. Okay, so is uniform. So maybe if you want to follow the talk from this point on, it will be easier to follow if you think about P as being fixed. But the point is that the dependence on P is explicit, and you can write it like this. And in fact, if you want n, if you're only interested in n reasonably large, then this R can actually be pretty small. No, it can be pretty small. It doesn't have to be very large. It has to be positive, but not terribly large. Yep. No, R is before P is mentioned. Yeah. So R is uniform. Don't hold me for this, but I think it's something like 7/41 for n reasonably large. Yeah. So it's really not that big. Okay, good. So this is what I want to talk about today. Now, for the purposes of this talk, I just want to say that I will completely ignore some complications that occur with small primes. So if P is 2 or 3, everything I say will be false, but morally true. And it can be fixed. I've done this all uniformly. But okay, so let me try to explain how you get a result like this. So let's go back to the zeta function. Here it is. So we want to estimate this at half plus it. So this is going to be something like 1/n to half plus it, except, of course, that this series doesn't converge. But let me ignore that. So in essence, the best estimates that we have for zeta of half plus it are obtained by estimating what we call exponential sums of this form, of the form sum of n to it, where n is in some kind of a range between m and m plus b, where I think of b being, like, say, between 0 and m or so. Right? And the idea is that, well, the trivial bound on this is b, because every term is of modulus 1. And then you want to beat that bound. In fact, if you use the trivial bound on this sum, and you go back to the zeta function, what that gives you is exactly the convexity bound once you apply the standard technology. Okay, now, how does that work in this case? So in the case of the L function.
I understand what you said in this exponential sum story.
Yeah.
Repeat that again.
Yeah, so I'm going to say, let's just forget about convergence. Let's just pretend that I can plug in half plus it here, which of course I can't, but let's pretend that. And this 1/n to half is just a smooth sum, so it's easily removed by partial summations. And so really what matters is that you want to be able to estimate the cancellations in the sum of 1/n to it, which is the same thing as that thing over there, right? And so you want to get a non-trivial estimate on that thing. What I said is that if you do use the trivial estimate, you will recover the convexity bound after you go through the whole analytic technology. Okay, now in this case, I'll tell you what happens in this case more precisely. So if you want to look at L of a half chi, as I said, this sum doesn't converge at the point half, right? But we have a standard technical device for this. It's called approximate functional equation. And what it says, morally speaking, again, this is not going to be really correct, but morally speaking, what it says is that you can write this as a sum of two sums. One is like chi of n over root n with a certain weight in n, which basically, morally speaking, ensures that this n goes up to something like, sorry, I'm going to make this m, just so as not to confuse things. So this m goes to p to n half. And then there's a dual sum, which I'm not even going to write. But it looks pretty much the same as this, just with the complex conjugate of chi. OK, so once you have this, it's a similar story. If you estimate this trivially, you say, OK, every chi is 1 in modulus. You have 1 over root m. You sum up to p to n half. You're going to recover p to n over 4. That's the convexity exponent, theta equal to 1/4. So the name of the game is to get non-trivial estimates for this sum. I'm going to call this sum S prime. OK, so we want non-trivial estimates on that. OK, now, if I want to understand this sum better, I need to understand what's happening with this character chi. OK, so recall that chi is a character modulo p to n. This is where I'm going to start using this in a serious way. So that means I'm looking at the group of z mod p to n z cross, i.e. the invertible residue classes in here. And this group actually splits as I can look only at those residue classes that are 1 mod p to n. I'm just going to say this consists of all classes A, such that A is mod p. Right, so I can look at the classes that are 1 mod p, and then it's going to be the direct product of this with a certain group that I'm going to denote by g, and this is going to be a cyclic group of order p minus 1. Okay, so this is cyclic order p minus 1. OK, so once I have this decomposition, if I'm interested in characters, I want to understand the dual group. So in order to, that means that this dual group that I can call gamma n is going to split accordingly as the dual group of this group of p minus 1 elements. And I'm going to just say the dual group of gn. And then I'm going to have the dual group of this guy, which is going to be a large group. Again, think about n as being large. So this is somehow the big piece here. And I'm going to call this gamma n1. So this is going to be characters that live on the group of residues that are 1 mod p. Right? So these are going to be characters of 1 plus pt. That's how they're going to function. And at this point, I want to say that because I'm thinking about p, let's say, as fixed and n going to infinity, I basically don't really care much about this part because it just has p minus 1 elements, right? So I'm going to concentrate on this piece. And here's a theorem that was in somewhat more elementary form. It was proved by Postnikov. So every character of this form is actually can be expressed in the following way. It's going to be E of, where this is the standard analytic notation. This is going to be e to 2 pi I x. Right, so it's going to be a complex exponential of a0 times the p-Adic logarithm of 1 plus pt divided by p to n for some a that's, so this constant a0 over p to n belongs to p to minus n zp. So it's some kind of it's a p-Adic integer times p to minus n. And you look at this, and before I move on, I'm going to call this character chi a. Before I move on, I just want to point out for people who haven't thought about this, this may look confusing. What is this? This is p-Adic logarithm, and then you're sticking it into a complex exponential. That's funny. But it's not funny because this is a p-Adic logarithm, so it's just going to have some kind of a power series representation. And eventually, you're going to get a very high power of p. And once you exceed p to n, it doesn't matter anymore because you're dividing by p to n. So it's going to be an integer. If t is an integer, from some point on in this power series, you're getting integers, so it doesn't matter for the complex exponential. So this is this is well defined. This is a character, obviously, because if you take a product of two 1 plus pt's, the logarithm is going to turn into a sum of logarithms, and then you get a product. So this is really a character, and you can actually prove that this correspondence that corresponds a to chi a induces an isomorphism of this group gamma n1 with p to minus n zp modulo p to minus 1 zp. So this is the kernel. If you take something in p to minus 1 zp, it's easy to see that the character you get is trivial. Okay, so this is an easy exercise. And so this gives you something to work with. And somehow something that I want to focus on is the fact that this guy here is a p-Adic analytic function of t. Okay, so this is where this is first occurring. Okay, so now with this expression in hand, I can go back to this sum, S prime. And I want to see what's happening in this sum. What I'm going to do is I'm going to split this sum according to residue classes of M modulo sum p to kappa. Eventually, I'm going to take kappa equal to 1. But before I do that, let me retain a little bit of flexibility here. So I'm going to take C modulo p to kappa, and the star means I'm only taking invertible classes. Okay, and then I'm going to have the remaining sum of chi of something like C plus p2 kappa m. Let me just see. Yeah, this should be enough. Okay, over square root of C plus p2 kappa m. And this m essentially goes up to p to n half minus kappa. Right, so basically, I've written everything as the residue class modulo p to kappa plus a multiple of p to kappa. This is easy. And the reason why I'm doing this is that now, because this chi is a character, I can go ahead and split it. I can get chi of c out, and I'm not going to care about that much. So I'm going to get chi of c. And then inside, I'm going to get the sum of chi of 1 plus p to kappa c inverse m times this weight function, which I'm not terribly concerned with for now. And m essentially goes up to p to n half minus kappa. And the point is, because this is now 1 mod p, these values are going to be given by something like this, right? So this guy here is going to be of the form chi a. So I can think of this as e of a0 times p-Adic logarithm of 1 plus p to kappa c inverse m over p to n. That's what we really have here. OK, so now the story is as follows. If I want to get a non-trivial estimate on my central value of the L function, I need to capture the oscillations that I get in this exponential sum. But I want to point out that at this point, somehow, you really have to learn to fight your intuition. Your intuition is completely wrong in this problem, at least if you're like me. Because somehow, if you go from m to m plus 1, this has nothing to do. Between m and m plus 1, you jump like crazy. But that's because it's the wrong neighborhood to look at. M and m plus 1 are very, very far p-adically, right? So somehow, this is close between m and, I don't know, m plus p to n third or something like that, right? OK. OK, so there's a lot of adjustment of your intuition that you have to do, but it can be done. OK, now, before I move on and explain what I did, I want to point out what people previously did and how the Weyl exponent was obtained. So what people previously did was they would take kappa to be essentially n over 3. Okay? So let me go here. So if you take kappa to be essentially n over 3 and a little more, I'm going to say plus big O of 1, what happens then in here, so think about this. This is the p-Adic logarithm. So p-Adic logarithm of 1 plus something is going to be that something plus that something squared, half, or minus, whatever. And then the next term is going to be this thing cubed. But the moment you cube this, you have p to 3 kappa. 3 kappa is going to be a little more than n. You divide by p to n, you have an integer. So you can completely trash that. And what happens is that you are left just with a quadratic polynomial in m here, right? So if you take this, if you make this choice, you're going to be left with something like, with some sums of the form e of at plus bt squared over p to n. And I'm not going to specify what these a and b are, but the point is it's a quadratic exponential sum. And at this point, you have a million nice little tricks that you can use on this sum. In particular, if you apply Weyl differencing just once, so what Weyl differencing does to this polynomial is it essentially replaces it with its derivative. You take the derivative of this, you get a linear polynomial. That's also known as the geometric progression. We know how to estimate these things.
So these things is summation by parts or what?
Sorry?
Is it summation by parts or is it a little bit more?
No, it's more involved. But it's a well understood device. And the point is that the special feature that occurs here is that you eventually land into linear polynomials, and you can just trivially estimate such things as geometric progressions. Now, that's wonderful. That leads to the Weyl exponent.
Yari, who mentioned that a few years ago, exactly the same set of characters that develop an issue of computing quickly. It's exactly as far as we got. Then he used fast Fourier transform and that fact that that's a data function.
Mm-hmm.
To obtain an evaluation which is better than the so the technique, Vincent, I was telling you about this yesterday,
Mm-hmm.
and all he quoted was possible.
Yeah. Okay. So what I want to point out is that this leads to this wonderful Weyl exponent, but it is also a dead end, because once you take kappa to be n over 3, you are never going to get anything better than the Weyl exponent, right? So it also somehow obscures the true nature of the problem, which is that this thing is a p-Adic analytic function. It is not a quadratic polynomial, right? Okay. So we go beyond this, and so what I have is basically a general method for estimating sums of the form E of f of m over p to n, where m is in some kind of an interval like this. And f is some kind of a p-Adic analytic function. More precisely, I'm going to take f to be a p-Adic power series, a convergent p-Adic power series. It's going to be of a specific form. I can later explain where this form is coming from. But basically, this f of t will need to have a leading term that essentially, the derivative of this f needs to have a leading term that's essentially of the form 1 plus p to kappa times omega t to minus y for some exponent y. I'll explain where this is coming from. And I'm going to allow this to be multiplied by some fixed power of w, and I'm going to allow some kind of a p-Adic unit here. These two things are p-Adic units, so omega and omega prime are just going to be in ZP cross. So you can think about them as being 1 for the time being. And unfortunately, I can't just stop here. I also have to allow some trash to appear in this function. But the idea is that what follows should not interfere with the fact that this is a main term. So there's going to be a term of the form p to w times some constant. And then I'm also going to allow some series g of t, which will need to satisfy certain conditions that I'm not going to bother you with. And this u will need to be large enough. And the point of these conditions that I impose on g, and the condition that u is large enough, is that this should never interfere with the main term. The main term should be what dictates whether I succeed or not. Okay. Now, in fact, it turns out actually that apart from finitely many primes, you can actually take this u to be as small as 1. Right? But at bad primes, you have to be careful about this. Now, why does this have anything to do with this problem? Well, if you take the derivative of the p-Adic logarithm, you're going to get something like 1 plus p to kappa t inverse, i.e. y is going to be 1 in that case. OK, so I'm going to impose these kinds of restrictions. I'm going to call this family of power series f. And what will happen is that I'm going to prove not one estimate, but actually a class of estimates of the following shape. So I'm going to say that a pair of numbers KL is a p-Adic exponent pair in analogy with the usual theory of exponential pairs. If the following holds, so
You might say that theory goes into the
yeah, so at the Archimedean case, there is a classical theory of exponent pairs, which was used to get improvements for the Riemann zeta function, and also it was used to break the canonical exponents in the divisor problem and the circle problem in classical analytic number theory. So if the following holds, so this sum, I'm going to call this sum S. So if this sum is less than p2 n minus w minus kappa over b to k times b to L. So this is morally what it should be. P2 n minus w is essentially the conductor here, and you also have to subtract this kappa. B is the length of the summation. And then you actually have to allow for a fudge factor. So I'm going to allow some p2r here, and I'm also going to allow the logarithm of p2n minus w minus kappa to some power. Okay? So if there exists r and delta such that this estimate holds for all f in f with n large enough, and for all b between 1 and p2n minus w minus kappa. So it needs to be completely uniform in B. Okay. I think I put it in the correct order of quantifiers. So KL is going to be a pair of numbers if the following holds. There exist two numbers r and delta, such that for every f in f with n large enough depends on the pair KL, right? Okay, and for every b between 1 and p2n minus w minus kappa, this holds true. Does that answer your question? Yeah. Now, I should point out that in the actual paper, I was actually much more precise than this, and I'm talking about p-Adic exponent data, which actually capture all the dependencies. But p-Adic exponent data contain like 10 pieces of data or something, so you really don't want to see it now. If you do, I'm happy to show it, right? But like this is somehow a compact version of that. So for example, here's a trivial exponent pair, 0, 1. Because if you have 0, 1, then basically you're estimating your sum by b, which I think we all agree holds. But the point is to get some non-trivial pairs. And the second main theorem is as follows. So the second main theorem is that we have two recursive processes which produce new p-Adic exponent pairs starting from a given pair. So it says that if k and L is a p-Adic exponent pair, then so are, so there's going to be two of them. One comes from what I call the A process. So A of KL, and it's the following pair. So the first guy is going to be k over 2 times k plus 1. And the second guy is going to be k plus L plus 1 over 2 times k plus 1. Caution, caution, if you are using Ivanets-Kowalski's book on analytic number theory, they have a different normalization of exponent pairs. So this is the usual normalization that everyone else uses. But yeah. But because that book has become so standard and it's a wonderful piece of work, I'm just saying, be aware. And the other process is B of KL, which gives you L minus half, K plus half. Okay, so let's get some feeling for these processes. So if you take this trivial exponent pair, 0, 1, and you apply the B process, so there's going to be the pair 0, 1. So if you apply the B process, you're going to get half-half. Let's try to understand what is this. If you go ahead and stick in half-half over there, b to a half and b to a half basically cancels out, and you get the conductor p2n minus w minus kappa to half. So this is some variant of the classical Poya-Vinogradov inequality. Poya-Vinogradov inequality tells you that if you take a character and you sum it in whatever interval, you get at most p2n half. So you recover this classical inequality. Now, if you apply the B process again, you go back to 0, 1. So that's not good. But you can apply the A process to this. And then you get 1/6, 2/3. OK, and then you can go ahead and play with this a little bit more. And so if you're lucky, you will hit this one. AB, A cubed B. So, well, lucky or desperate enough. Anyway, if you, if you play with this for long enough, you will capture this one, which, if I'm not wrong, is 11 over 82, 57 over 82. And this one will be actually pretty important. OK, but yeah, you can keep playing. That's acceptable.
You don't get down to 0.
Yeah, yeah. So ideally, one would want something like 0.5. That would be wonderful, but tough luck. OK, so now why is this good? What does this have to do with that problem? Did you have a question? Yeah. Yeah, I'm getting there in 2 minutes. If you mean in terms of the L function. Yes, I'll explain that. Just give me a minute. So, so what does this have to do with that? Well, OK, so now you can estimate sums that occur over there, right? So I have a sum that's essentially of the length p2n½ minus kappa. So this is the essential range. This is where it's really important to have good estimates. And you can go ahead and stick that in here. There is this smooth cutoff function, but it's not a problem. It's just summation by parts. You can eliminate that. That's not a problem. And if you go ahead and you stick that estimate over there, what you get as a result is that L⁴ chi can be bounded from above by, there's going to be a fudge factor that I'm going to write later. But the point is that there's going to be the power of p2n, which is going to be the following power, k plus L½ minus 1/4. So that's the exponent that you get. There's going to be a power. There's going to be a power of the logarithm of this, which I'm completely going to ignore here. It can be tracked, but it's not that important. And then there's going to be a power of p, which is actually the following power. It's p2r, where r is this guy that you have over there. And then there's also plus kappa times 1 minus k minus L. So you can go ahead, use summation by parts, use your estimate on the p-Adic exponential sums, and you get this kind of a result. OK, now here's the bottom line. What do we want? We want this exponent to be as small as possible. Right, so we want k plus L as small as possible. OK. Well, OK, this is k plus L is 1. And that gives you exactly ½ minus 1/4. That's the convexity exponent. So you get nothing. And pretty annoyingly, this also gives you nothing. But that's because basically the approximate functional equation already has the duality built in. So OK, here's the biggie. So if you take this one and you plug it in, 1/6 plus 2/3, that's 5/6. Divided by 2, that's 5/12. Minus 3/12, that's 1/6. So this basically leads to the Weyl exponent. And the name of the game is to improve on this. But before I do that, I just want to point out that all that happened here was one application of B process and one application of A process, which is way easier than 2 applications of the A process. Because to apply the A process once, somehow you only see some easy features, especially because there are these special cancellations with geometric progressions and such. So to get the A process into a recursive shape is actually seriously analytically difficult. OK, now, as I said here, if you take this guy, k plus L is going to be 5/6. So you have to break below 5/6 in order to get those better results. And that's provided, for example, by this one. So in this case, k plus L is 68 over 82. And it's not entirely obvious, but yes, this is less than 5/6, a little bit. And this leads to the result of theta. Well, I really should make this big because it's kind of my main result. So this gives you theta that's 27 over 164, where 1/6 is 27 over 162. So this is less. This is less, and this is 0.1646. Okay, you will notice that this is a little bigger than, where's my 1645? Have I managed to erase it? Yeah, so in my main theorem, theta is allowed to be anything bigger than 0.1645. So you can gain a little more than this by inventing new exponent pairs here, right? So to answer your question, so you had a question of how small can these things get. So the relevant question really is how small can k plus L get, rather than individually, right? And this question was considered way back by Rankin, because these two recursive processes that I have, they formally agree with the recursive processes for the classical theory of exponent pairs. And so Rankin considered this question, I must imagine, hoping that he will prove that you can get a sequence of exponent pairs for which this theta goes down to 0. Okay, but no, unfortunately, he found something else. He found that there is actually a hard limit. You can get lower and lower, so there isn't like somehow there isn't the optimal pair. But you can get lower and lower, and there is somehow an infimum which is less than this by 0.0001. Right? So yeah. So actually, I don't know, do I have the other one? Yeah, I don't think I wrote it here. But like, you can like iterate. I think the next interesting one is something like ab, a cubed b, a squared b, a squared b. And if you do that one is due to Phillips. You get your improvement by 0.0001. But it's kind of like there is a hard limit as to how far this goes. Sorry? Oh, so these are further methods, and somehow the big improvement was really obtained by the method of Bombieri and Divanets, and then Huxley kind of really got to the bottom of that method and got some additional cancellations there. Sorry? Yeah, it can be obtained by A and B processes. You have to go further. Okay, good. So that's kind of what I wanted to say about this. And another thing that I want to point out here is that when you get these estimates, picking.
Gary and Ivanich, from my discussions with him, decided they want to end this sequence of small improvements, and I think they just didn't. I mean, Huxley was able to.
Yeah.
Nobody could concrete. So kind of got to kill the sequence.
Yeah. So I just wanted to point out that in order to get these pairs, the value of kappa that you choose doesn't matter. That's kind of interesting. Even though it doesn't look like that, it looks like, oh, there's some contribution with kappa. But R also depends on kappa. And in all of the pairs that I constructed, these two basically exactly cancel each other out. And what you take for kappa doesn't matter. And eventually, you can take kappa to be equal to 1, for example. So somehow, I really don't rely on the fact that this is like a quadratic or a cubic polynomial or something like that. It is really a bona fide p-Adic analytic function for me. OK, so any more questions?
Yeah, what is your method?
Yeah, so I was going to now try to explain this. So, so how do you get these things? OK, so instead of trying to rush through both A and B methods, which would be way too ambitious, especially in light of the soccer game, I'm going to try to sketch what happens for the B process here. So how does one obtain something like this? OK, well, first of all, you have to have a game plan. And the first idea is that, well, if I apply the B process once, this somehow corresponds to the Poev-Vinogradov inequality. And if you think about the classical Poev-Vinogradov inequality, that's basically just one application of Parseval's identity, right? So this has to do with some kind of a duality and Fourier analysis. So if you want to do that, you will need to understand the Fourier transform of f, the discrete Fourier transform of f. So f lives modulo p to n. So I'm going to look at the Fourier transform that I'm going to denote as EF hat of s, which is just going to be sum over all m modulo p to n, E of f of m over p to n. That's my function. And then I'm going to have minus Sm over p to n for the Fourier transform. OK. And the idea is that what I'm having is some kind of a sum of E of f of m over p to n with some kind of a weight that I'm not going to write down. I mean, I can think of this as a sharp cutoff. So it's like between m and m plus b. And I can go ahead and apply Poisson summation to this. And this is going to relate this sum to the sum of E sub f hat of s times some weight in s. right? Okay, so basically my idea is to pass from this sum to this sum. And if I want to be effective in estimating this sum, I need to understand this as a function of s. Right. Now, if I look at this sum, here is one feature that I want to point out. This sum is a complete exponential sum modulo p to n. So this is very different from the initial sum. And because it's a complete exponential sum, this is kind of like something that people in algebraic geometry look at and try to estimate. And one method that you may want to apply is the method of stationary phase. So here we apply p-Adic stationary phase. Which basically means the following. I'm going to split this sum over small p-Adic neighborhoods. So I'm going to look at m. That's going to be of the form maybe m0 plus p to jt, where this m0 is going to be fixed. It's going to be a center of a p-Adic ball of radius p to j. And I'm going to let t vary. Right? Now, why would you ever want to do this? Well, because then, if you go ahead and you use the Taylor expansion around this point, you're going to get f of m0 plus p to j times f prime of m0t, and then plus the remaining stuff that's going to have p to 2j. Okay? And so if I take j to be a little bigger than n half, if I take j to be just a teeny bit bigger than n half, then this is going to be just a teeny bit bigger than p to n. And therefore, it won't matter at all in that sum. Right? So the upshot of this is that with this choice, if I take a ball that's this small, then inside this ball, this sum is basically just going to have this linear term, p to j f prime of m0t. And there's also going to be a linear term coming from minus sm. Right? OK, well, if you have a complete geometric progression, like a complete exponential sum that's a geometric progression, then that's basically going to be 0, except if your quotient is really an integer. Right? And what this means is that this is going to reduce this sum, E sub f check of s, only to those m for which f prime of m0, or f prime of m should be 0 mod p to n half, essentially, plus big O of 1. Because, right, I have p to j here, and I will need, sorry, this is going to have to be, yeah, s, sorry. Thank you. So basically, the idea is that after you subtract these things, this p to j f prime of m0 needs to cancel out what I'm getting over there. And this is basically p to n half. So this will also, this minus s will have to also be basically divisible by p to n half. And I'm going to get that same thing over there. OK, so we are now in a situation where this initial complete exponential sum has been written as a sum over what I would call approximate critical points of this function f. OK, now when you have something like this, you have to answer two questions. This is a crucial point. So the first question is, OK, this is an approximate critical point. Is it actually close to an actual critical point? OK, so that's somehow the first question. Maybe I can go here. So question 1 is S close to an actual critical point? And the second question, I mean, critical points don't bring happiness if they are singular. So the second question is, if so, then is this critical point non-singular? And if you want to answer whether a critical point is non-singular, that ultimately is some kind of a non-vanishing condition that you can write down. But the problem is that because we're going to do this recursively, and we're going to have a squared b, ab, a cubed b, as you go through these recursions, these non-vanishing conditions become horrible to write down. And so this is somehow one big feature of that class of functions that I defined initially. So that class of functions has this property that no matter how many times you churn through A and B processes, you can show that the critical point that you get is actually non-singular. And once you do that, you can, so the answer is yes and yes after you smartly define your universe. And once you have that, then you can go ahead and you look at this f prime of m is, let me just say, equal to s, right? Where this s is somehow where things actually happen. And you can look at this equation, and you want to solve for m as a function of s. So what you will need is the p-Adic implicit function theorem here, which I developed for this class of functions. And what this will show is that you can solve this, and you will get that m is some kind of a, let's say, f twiddle of s. So this is going to be some kind of an inverse function. In this case, where this f twiddle is also in my class f. Okay. Okay, now I'm going to take this m, and I go ahead and I stick it in here. Okay, so if I stick it in here, I'm going to get something that depends on s only, right? But this is happening over the whole p-Adic ball inside here. Now, this is the same as what happens in real analysis when you are close to a critical point, and if you are non-singular and everything, then this is eventually inside this neighborhood. This is going to be modeled by a Gaussian, right? You get the quadratic term which dictates how you do this. And the p-Adic Gaussian is just a fancy name for a quadratic Gauss sum, right? So you get a p-Adic Gaussian, and you can actually explicitly evaluate what you get here. And the result is that this Fourier transform, it's stunning. You really don't expect something like this in analytic number theory, but life is sometimes good. What you get is that this f hat of s is going to be given by some kind of a unit times p to n minus w plus kappa half. This is the modulus of that sum, times a single complex exponential of a function that I'm going to call f brevi of s over p to n, with some function f brevi that's also in my class f. So this is a wonderful compact evaluation that tells you that you can take that complete exponential sum, and you can exactly tell how large it is and what is its argument. Okay? And once you have this, you can go ahead and you can stick it into this duality formula. And we get a wonderful summation formula that I want to share with you, and that's kind of going to provide some closure. So you get a summation formula of the following form. I'm going to state it with a smooth cutoff, which is really where you can see what's going on. So on the left-hand side, you get the sum, let's say, over all m in z, e of f of m over p to n times some smooth function h of m over b. So this is like an exponential sum, essentially of length b. It's just that it's smooth. Okay? And what I'll get on the other side is the sum over all t in z of e of some other function that I'm going to call f math ring. That's how it's done in LaTeX. So f math ring of t over p to n times a certain transform of h. So h transform fb of t over I shouldn't be here, but OK. p to n minus w minus kappa over b. And then this side is also multiplied by, I forgot this, so there's also the size, epsilon b over p to n minus w minus kappa over 2. Okay, this is on the right-hand side. Okay. Okay, and so it is an exact explicit formula. There is no error term here. And the point of this is that there is duality in the following sense. If this is of the length b, this is essentially of the length p to n minus w minus kappa over b. So if you have a long sum here, you're going to end up with a short sum here, and conversely. And before you tell me, OK, but we've seen this a million times, this is just Poisson summation, remember that this is p-adically exponential. This thing is p-adically analytic, which means that somehow real analysis has pretty much nothing to say about a sum like this. You really have to fight to get a form like this. OK, now, in order to, basically you can recover the B process from here by unsmoothing everything. These are smooth sums. You have to unsmooth everything. But the bottom line is that from a sum of length b, you can go to a sum of that length. And then if you apply the known exponent pair kl to what you have on this side, you will recover the B process. And I want to say, before I finish, that you would expect that something like this would only enter in the B process. At least I would expect that. But actually, A process turns out to impose some very serious analytic difficulties in terms of the dropping of the conductor and everything. So to write it as a recursive process introduces some difficulties that you don't see when you just write it to do it once. And in particular, it turns out that in some ranges, it is actually beneficial to use this summation formula also in the proof of the A process. OK, so that's all I can say. Thank you very much.